If you're from a city like Karachi where three-wheelers are common, and riding them is extremely unsafe and often feel outdated, well, our team at Habib University have found just the solution by designing a stable, sustainable, and smart electric trike, which is a three-wheeler vehicle, by integrating real-time telemetry using Verilog and the Basys-3 FPGA board. This project tackles safety with an advanced suspension and lower center of mass, and efficiency through live speed and distance tracking. This project was built using repurposed scrap that supports sustainability. The primary features of the hardware are its low center of gravity, a hub motor for propulsion, and a minimal suspension system that was made from recycled parts. All electronics were also cleanly integrated on the chassis, keeping it minimalistic. The low center of gravity solves our prime issue of trikes flipping over. This project is also sustainable, economical, and totally carbon emission-free. The core is the Basys-3 FPGA, which receives input from Hall-effect magnetic speed sensor placed on the rear wheel spoke. This sensor then sends digital pulses to the FPGA, which calculates speed and distance in real time. Our Verilog design includes a pulse counter, FSM, lap timer, and debounce logic. These modules work synchronously to provide accurate and smooth data on screen. By using Verilog, we have developed a fully custom game-like FPGA display system as well. It cycles through 3 states: home, running, and end, all of which are managed via a finite state machine. Speed, lap time, and distance are rendered live using character ROM, coordinate mapping, and pixel timing logic. The visuals help gamify the riding experience by tracking high scores and lap completions as well. All of this is primarily managed by the control unit in our overall system design. The finite state machine of the control unit starts with idle, which is our home screen, which displays start engine, and transitions to running when the start button is pressed. Running, which is our main screen, activates Hall sensor pulse counting and displays real-time speed, distance, and timer. It then transitions to end when the trip completes, which means the lap is completed. The END, which is our high score screen, shows lap time and compares it to the high score. Then resets to idle after a delay or button press.
Now the demonstration.
The initial display screen shows start engine, which is waiting for the input from FPGA button to initiate the program when the trike starts running. As soon as the start is hit and the user throttles, the timer on the screen also starts counting seconds and minutes as well if necessary. The lap distance is set to 1,000 meters. The distance traveled by the trike is calculated using this formula and additions 20 when it covers one rotation into the total lap distance covered by the trike. Additionally, a speedometer is also integrated, which uses this formula to calculate the trike's speed and keeps updating it with time on the VGA screen. Our system achieves ±0.5 km/h speed accuracy and sub-millisecond update delay. When the lap is covered, the game ends and displays an end screen which shows the time in which the user covered the lap. If this time is less than the time taken to cover one lap in the previous run, the high score is updated for the next run. The next stage is initiated when the reset button on FPGA is pressed, which sends the screen to the start engine stage again. The wiring harness of the trike starts from the sensor sending signal to FPGA, throttle signal to the motor controller, while the VGA cable is used to show display on the monitor. The wiring is done through metallic bars for minimalism. For the integration with hardware, the FPGA board is mounted near the handlebars in a weatherproof enclosure, allowing for easy accessibility and monitoring during operation. It receives real-time input from the Hall-effect sensor, which is mounted near the rear wheel hub and sends digital pulses corresponding to wheel rotations. To ensure stable performance, the FPGA is powered via a 5V buck converter connected to the main battery system, which provides regulated voltage supply even under varying load conditions. The Basys-3 provides 3.3 volts and ground on all PMOD connectors. Hall sensor is declared as an input and mapped to P17 in constraints, XDC, file. This project not only demonstrates the practical application and implementation of digital logic and design concepts, it also offers a scalable, eco-conscious solution for urban mobility. By combining sustainable hardware-level logic precision, we have built more than a vehicle. It is a foundation for a much smarter and safer transport system. Thank you.